Okay, our next topic is coefficient of viscosity of gas, which is represented by eta. Just as liquid, a gas shows the property of viscosity, by virtue of which a liquid or gas possesses relative motion between different layers. The coefficient of viscosity can be defined as the viscous force per unit area per unit velocity gradient, and its SI unit is Newton second per square meter. Okay, this is the definition of coefficient of viscosity, that is the viscous force per unit area per unit velocity gradient. This is the definition of coefficient of viscosity, and its SI unit is Newton second per meter square. Okay, now for this, suppose a gas is flowing along horizontal surface. In figure we can see that there are three layers A, B, C. Now suppose for this gas is flowing along horizontal surface. Let the horizontal surface be taken as X, O, Y, that is the horizontal plane, and gas is flowing from left to right. The layer in contact with the surface is at rest, that is the layer which is in contact with the lower surface is at rest. This is the consideration. Now the velocity of the layer of the gas increases in the direction of z-axis. Along z-axis, the velocity of the gas increases. In a particular plane, the velocity will be the same everywhere. That is, along plane, horizontally, the velocity of all the gas molecules will be same at a particular distance from plane X, O, Y along z-axis. Now let A, B, C be the three layers of gas. We are considering here the gases layers, and we are considering for our consideration, for our simplicity, there are three layers of gas A, B, C, separated by distance lambda. The mean free path of the gas molecules, that is the mean free path of the gas molecule, एवढ्या separation ना ते separate आहेत तीन layers. Let V be the velocity of gas in layer A. If dV upon dz is the velocity gradient along z-axis, then the velocity of gas in layer C will be V minus lambda dV upon dz. Here dV upon dz represents the velocity gradient along z-axis, that is change in velocity with change in distance along z-axis. Therefore obviously the velocity below plane A, फिगरमध्ये जे प्लेन ए दाखवलं त्याच्या खालची कशी असणार, तेवढ्यानेच वेलोसिटी कमी असणार आणि त्याच्यावरची तेवढ्यानेच वेलोसिटी जास्त असणार. Therefore the velocity of gas in layer C will be V minus lambda dV upon dz, and that in layer B will be V plus lambda dV upon dz. Hence the distance between the layer is equal to the mean free path. Since the distance between the layers is equal to the mean free path, when the molecule moves from one layer C to A or from B to A, the molecules travel without collisions. Though the molecules are moving at random in all directions, it can be assumed that about the 1/3 of the molecules are moving along each axis. 1/6 can be moving along the positive direction and 1/6 along the negative direction of the coordinate axis. Now suppose let n be the number of molecules per unit volume of the gas, m be the mass of each molecule, and c be the root mean square velocity of the molecule. Then consider a unit area in the layer A. Then the number of molecules from layer B crossing the unit area of A in unit time in forward direction is 1/6 nc. आता या ठिकाणी बघा, c is the RMS velocity, root mean square velocity, आणि या ठिकाणी n घेतलेला आहे नंबर ऑफ मॉलिक्युल्स पर युनिट व्हॉल्यूम ऑफ द गॅस, आणि या ठिकाणी कन्सिडरेशन केलेलं आहे, इट इज अजून दॅट अबाउट 1/3 ऑफ द मॉलिक्युल्स आर मुव्हिंग अलॉंग ईच ॲक्सिस. 1/6 त्याच्या अर्धे पॉझिटिव्ह डायरेक्शनला आणि त्याच्या अर्धे निगेटिव्ह डायरेक्शनला. इट मीन्स दॅट नंबर ऑफ मॉलिक्युल्स फ्रॉम लेअर बी क्रॉसिंग द युनिट एरिया ऑफ ए in unit time in downward direction is 1/6 nc, and the corresponding mass transport will be 1/c, that is the corresponding mass means फक्त त्याला एका मॉलिक्युलच्या मासने मल्टिप्लाय केलं तर आपल्याला मिळते corresponding mass transport from layer B to layer A will be 1/6 nc. Therefore the total momentum transported by the molecule moving downward from layer B and crossing the layer A per unit area per unit time will be त्याच्या फक्त व्हेलॉसिटीने त्याला मल्टिप्लाय करावं लागेल. दॅट इज mnc अपॉन 6 इंटू व्हेलॉसिटी दॅट इज v प्लस लॅम्बडा dv अपॉन dz. Therefore, similarly total momentum transported by the molecules, त्याच पद्धतीने जसं a to b, b to a केलं आपण तसं c to a. Similarly total momentum transported by the molecule moving upwards layer c and crossing the layer a per unit area per unit time will be mnc upon 6, फक्त velocity change होणार v minus lambda dv upon dz. Therefore the net momentum lost by layer b and hence gain in momentum by layer c per unit area per unit time will be mnc. एकातून दुसरा मायनस करावं लागेल. तर वरच्या इक्वेशनमधून खालचं इक्वेशन मायनस केलं आणि आपल्याला मिळालं इक्वल टू 1/3 mnc लॅम्बडा dv upon dz. Therefore the change in momentum per unit time in the force, change in momentum per unit time is the force. We know that dp upon dt, that is the change in momentum with time, is called a force. This force is due to the viscosity of the gas. The viscous force acting on the layer is proportional to the area A of the layer and the velocity gradient dv upon dz. That is, force is directly proportional to the area of the layer and velocity gradient dv upon dz. Therefore f equal to eta into a dv upon dz, where eta is the constant called as the coefficient of viscosity of the gas. Therefore we know that f equal to viscous force per unit area, that is f equal to f upon a equal to eta into dv upon dz. Okay, that is the force, and force per unit area is the viscous force per unit area, which is given by here small f. Now compare, if we compare equation 1.2 and 1.3, what we get? n dv upon dz equal to 1/3 nmc lambda dv upon dz. Therefore eta equal to dv upon dz cancel होऊन जाणार 1/3 mnc into lambda. But m into n is the density जे आपण मागच्या आत बघितलं, mass into number of molecules per unit volume, that is equal to density of the gas, that is eta equal to 1 upon rho c lambda. Now dependence of coefficient of viscosity on pressure and temperature. When the temperature of gas is constant, its density is directly proportional to the pressure, but the mean free path is inversely proportional to the pressure, and so rho lambda remains constant. हे आपण मागच्या आत बघितलेलं आहे. ह्या गोष्टी कॉन्स्टंट राहतात. Thus, so long as the temperature is kept constant, the coefficient of viscosity does not depend on the pressure of the gas. That is, जोपर्यंत टेम्परेचर कॉन्स्टंट राहणार, the coefficient of viscosity does not depends on the pressure of the gas. The RMS velocity of the gas molecules is directly proportional to the square root of the absolute temperature. हे पण आपण बघितलं इक्वेशन. Therefore from equation 1.5 eta is inversely proportional to 1 upon eta is inversely proportional to root t. हे आपण इक्वेशन बघितलं. eta is equal to 1 upon 3 rho c lambda, that is we know that c is directly proportional to the root t. Therefore it means that eta must be inversely proportional to root t. Thus the coefficient of viscosity of gas is directly proportional to the square root of its absolute temperature.